Good morning, YouTube. We're back. All right, so what we're going to do today is we're just going to summarize all the Pythonic math we did this week. This will be your last Python screencast for the year. In fact, this is the last day of the school year. We have graduation later this afternoon, so summer starts, I guess, after that. Alrighty, so now remember what you need to do with a calculator. So can you replace the calculator with Python? Yes, because remember what you have to do. Well, all right, let's start. Let's do a pound bang. Make that a little bigger. Make that really big. Okay, pound bang. User bin Python. Directory USR, directory bin, and executable Python. Okay. All right, so the first thing I'm going to do, all right, so these are the four things you have to do. You have to be able to graph in an arbitrary window. I'll leave that to last, so I have something to graph. But what that basically means is you have to be able to evaluate a function at any point and then graph those points, right? So the first thing I'm going to do is define a function. Okay, so let's define a function. Define a function like, for example, f of x is x squared minus 2. A perfect example we could use with Newton's method to figure out the square root of 2, which is a root of that parabola, right? Okay, so what I'm going to do is I'm going to define the function this way. It's more than one way to do it, but there you go. Am I in Kate? Yes, I am. Oh, I didn't save this. Let me save this. File save as. So I just get my color coding and everything, and my indentation, stuff like this. So 2016 executive summary. Here's your executive summary for Pythonic calculus. There you go. That'll do. Okay, and there you go. Good. So let's return. Well, x squared minus 2. Okay. Now let's test that. So print. Let's see what I'm going to label this as. How about the square root of 2 squared minus 2? Aha. Equals. Or I could have just said f of square root of 2, right? So, but, whoops, wait a minute. I need another parentheses here. Well, actually, I could live without this parentheses. Bing. Okay. Let's see, so quote, comma, and let's do f of square root of 2. All right, now, do you see the problem? I'm probably going to have to import square root, right? Well, just for fun, let's do a save, Control S. Let's go to the shell. Where is it? There it is. Let's do an ls-l star.py just to see what we got. And it did that thing again. I hate when it does that. File save as home. I don't want it there. I want it in home. Okay, there. All right, so let's try that again. And so we have to change mode. 2016 summary.py. Whoops, to 755 executable, right? So let's see, and let's list again, and it's okay. So now let's run it. 2016 summary. By the way, everything we're doing here you can do in idle, and everything we're doing here you can do in Sage, except for the plot command, because Sage has its own plot command. I'm going to make a plot command or later based on Turtle Graphics, and Turtle Graphics is installed when you install idle. It doesn't come with native Python, I don't think. So, .py. And do we get this error? It doesn't like line 4. What? I didn't expect that error. I expected an unknown sqrt. 1, 2, 3, 4. What? What is going on here? Wait, hang on. Let's start over. Let's see. Define f of x return x squared minus 2. Okay, and then let's print quote, how about f of the square root of 2? Alright, let's try that. Save it. Let's try that. What am I doing wrong? I'm doing something stupid. No such user been... Oh, I said pound bang and I wrote bang bow. Pound. It doesn't know Python. Sorry. That's why. Oh, somebody errors a little time. Sorry. Okay, wait, let's save that. And... aha, squared is undefined. Alright, so now remember how we did this yesterday. You could import math and do math.squared everywhere you see squared, or you can, let's put the imports up here. Let's do from math import square root. So you don't have to write math.square root, just write square root. Another way to do imports, import specific functions, one at a time, instead of the entire library. And perfect. And that's basically 0. Isn't the square root of 2 squared 2 minus 2 0? So that's basically 0. This, remember, we have a lot of round-off error because we're converting everything to binary on the computer or on a graphing calculator. There's always round-off error, so we always tell the kids to round off to 3 places, right? So that to 3 places, that's 0.000. That's fine. Okay. Alrighty. Now, let's do. So what else do you have to do? So you have to be able to graph in an arbitrary window, which means you have to be able to evaluate functions. We'll get to graphing later. You have to be able to get a numerical derivative, a numerical integral or definite integral, and you have to be able to get roots. Okay, so how about we start with numerical derivative, and then we can use Newton's method and our derivative function to get roots, and then we can do integrals, and then we can do graphing. Okay, so there you go. So let's do derivatives, right? So number 2. And by the way, it's really only going to be 4 things that we're doing here. 1 and 5 plotting go together, but that's okay. I need a function to work on anyway. So number 2. Let's say find the numerical derivative as a limit. Find the numerical derivative. So we're also doing limits here. By the way, there is a limit command in Sage. If you're not doing pure Python, you can use a limit command if you want. Find the numerical derivative as a limit or a convergence table, right? Using a loop. Okay, so first let's define what a derivative is. Define diff of x comma h as returning f of x plus h minus f of x, right? Remember the differentiable filk on YouTube. That quantity divided by h. Alrighty, so now that's it. Let's do a print to separate the output from number 1. So blank print line, and then print. Let's see, what do I want to do? Let's find the numerical derivative of f of x at 2. Okay, so find. Well, how about f prime at 2? How about that? Now think about it. F prime, if f is x squared minus 2, f prime is 2x. If you plug in 2, you're going to get 4, right? Okay, so let's do this. How about that? Find f prime of 2, or alright, how about this? Let's just label it very simply equals whatever we get from this convergence table, okay? So how about this? For x in range, let's do 5 iterations. Whoops. Alright, let's print the diff. You call it whatever you want. I called it diff like Sage does, but you can call it derivative or ender like the T83, 84 calculators do. But anyway, diff of, let's see, at 2, and then let's make h really small, powers of negative x, where x is 0, 1, 2, 3, 4. Okay, so when x is 0, the h is 1. When x is 1, the h is a tenth, or 0.1. When h is 2, when x is 2, h is 0.01. When h is 3, when x is 3, h is going to be 0.001, and when x is 4, h is going to be 0.00001, right? Okay, and I guess that's it for the numerical derivative. Let's see if that works. Save it, Control S, go back to your shell, up arrow twice to clear it, up arrow twice to run it, and then we say it should be around 4, and you can get as many digits as you want after the 4 to be zeros, right? So all right, that's it, done. And as we're separating, we're labeling our work. F of square root of 2 is approximately 0. F prime of 2 is approximately 4.000 if you round off to 3 places. You want a convergence to 3 places, you can go range 5 if you want. Go a little longer. Okay, perfect. Okay, now number 3. Oops. All right, what's number 3 going to be? Find roots using Newton's method as a limit. Okay, find roots using Newton's method as a recursive limit, right? There's a recursion. All right, so let's define root, or newt, or whatever you want to call it. Define root, right? I mean, you could use find root in Sage. You can use solve with a .n, that kind of thing. Define root. Now remember, what you do is you start with a certain guess, and then you make the guess better, right? So how about we return, let's see, what is it? The old guess minus f of that guess over diff of f at that guess. And now let's default h to something small. How about a millionth? There you go. And so diff will not be exact. It's accurate to the millionth, right? For h is a millionth. But the recursion will still approach the correct answer, right? So what's the root? In other words, this is a classic Newton's method problem. When is x squared minus 2 equal to 0? When x is rad 2 or negative rad 2. So we can estimate rad 2 this way. Okay, so let's do that. Let's do a print. Print. Just separate the different problems on the output screen. Okay, and let's see, let's label our work. The root of f of x is equal to 0 near x equals 1. Okay, how about this? Solve f of x equals 0 near, what's our first guess? X equals 1. How about this? The closest root of f of x equals 0 near x equals 1 is. How about that? Okay, let's do it like that. Okay, so now let's start with our guess is equal to 1, and then for x in range 5, whatever you like. Okay, and let's move this down a little bit. Okay, move this up a little bit. All right, let's print the current guess. So it'll print the first guess, then change it, and then the new guess is going to be root g. So the new guess is going to be the old guess plugged into root, which does this, right? That's exactly what we want. And let's see what that does. Okay, this doesn't return anything. This is what we used to call in Pascal a procedure, because it doesn't return anything, it just prints stuff. As opposed to this function, which returns something, we call that a function, right? So anyway, so it's sort of procedural. So let's save it, and let's see what we get out of that. And so we get an estimate of rad2 is about 1.414. Look at the convergence. 414 all match up. That's nice. Okay. So the closest root of f of x equals 0 near x equals 1 is, okay, f prime of 2 is about 4, f of square 2 is about 0, the roots of f of x is equal to 0 near x equals 1 is, and if we change it to x, the original guess is -1, we'll probably get the negative root, but there you go, let's not get too crazy. Alright, let's do a numerical integral. Number 4. Alrighty, so find the definite integral as limit. Okay, fine. So these are all limits with these 4x in range 5s. These are all the convergence tables. So find the definite integral find the definite integral as a limit. Well, back up. Limit. Okay. Alrighty. On this one, you can make a function for L sum if you want, and R sum and trap sum, but we didn't do it that way. So let's just go print. Okay, so let's see. The definite integral of x from 0 to pi. How about that? The definite integral of f of x from a equals 0 to b equals pi just labeling our output is, okay, let's do this loop. How about we let a equal float 0, okay, so it doesn't default to an integer. Okay, where am I? There I am. Alright, and b equals pi. Now I think pi is in the math library, so you're going to have to add to the import line probably, but there you go. Let's just pretend that's not a problem. Whoa, what was that? I just want pi. B is pi. Okay, now for x in range 5, let's say 5 is not enough, we can make more. Let's find, let's say n equals 10 to the x. Alright, so again, range 5 generates x equal to 0, 1, 2, 3, 4. It's like a sequence in math class. And the sum of the sequence, sum would be a series, right? So when x is 0, you get 1. When x is 1, you get 10. When x is 2, n is 100. When x is 3, n is 1,000. When x is 4, n is 10,000, right? Okay. And so we can figure out the height of each trap, or the width of each base of each rectangle, is b minus a over n. Okay, good. And then your L sum, your left sum, is the sum, of the list or the series. So the sum of the series is going to, the sum of the sequence is going to be a series. And here is the sequence. F evaluated at a plus I times h, that's the height of each left rectangle, times h, that's the width of each rectangle, or base of each rectangle. Let's see, for I in range n. So you can do n rectangles, so 1 rectangle, 10 rectangles, 100 rectangles, 1,000 rectangles, whatever you like. Okay, and then we figured out that R is simply L minus the first left rectangle, which is f of a times h, plus the large rectangle that, the last rectangle that R sum uses and L sum doesn't use, f of b, times h. And then so it converges, quicker, or quickly. What the hell is this? Let's print the trap sum, which is simply L plus R over 2. All right, let's see what that does. Now, who knows what this is? Let's see. Now, remember what the function is. The function is x squared minus 2. Okay. All right. Now, the integral, the indefinite integral would be x cubed over 3 minus 2x plus c. Right. If you want to evaluate that from a equals 0 to b equals pi, don't you get pi cubed over 3 minus 2 times pi? Let's see if that's what we get. All right. So did I save this? No. See this little green thing up here says I didn't save it yet. Control S. There it went away. And let's clear this field. And let's run it. And pi is not defined, like we said. Okay, so let's go back up here and just comma pi. And we should be okay. I think that constant is, all lowercase, is defined that way. Control S. Go back to your shell. Clear it. Clear the shell and run it. And 4.052-ish. Now, who knows if that's right? Is that pi squared over 3 minus 2 pi? Let's find out. What if we went to the graphing calculator and tried it on there? Let's see. Come on, load already. Alright, so let's make a, let's make a document. Let's make a calculator document. Let's go to Menu, Calculus, Integral, from 0 to pi. Let's see, well, just for fun, let's not put limits of integration. Can I do an indefinite integral here? What did I want? I wanted x squared minus x. I could do this on 83 or 84 if you want to. Whoops, I know. I forgot the dx. And there it is, like we said, plus c, it doesn't do. Okay. But, can I edit this? Just add limits of integration? No, I can't. Okay, so let's do it again. So, Menu, Calculus, Integral, from 0 to pi. Okay. Of x squared minus x. I probably should have defined that as f of x somewhere, but whatever. X squared minus x with respect to x. And does that look like pi? Let's see, pi cubed over 3 minus pi squared over 2. Wait, did I do something weird here? Oh, it's minus 2. What am I doing? Sorry, I did something stupid. Okay, wait. What we're integrating is this minus 2, right? Okay. I mean, I could have been minus x, but that's not the example we're doing. So minus 2, and you get, right, x cubed over 3 minus 2x, like we said. And then this, we're going to integrate it from 0 to pi, but with x squared minus 2 again. Alright, does that look like x cubed over 3 minus 2 pi? Well, isn't 2 pi 6 pi over 3? Yeah, that's what it is. And numerically, what is it? 4.052. Let's see, 4.052 is exactly what we got. Okay, and we even have a convergence there. In fact, I have more convergence. I have 4.05224 is matching up, so I have even more accuracy than I need. Okay, now, so that's your numerical integrals. Okay, let's go back to plotting. How does the plot command work in Sage? Well, let's see. So number 5, just for fun, let's also plot the tangent line at a point, let's say at x equals 1. Alrighty. Let me see. Let's say we do, like the first tangent line from Newton's method starting at x equals 1 or g equals 1, that process. So let's do some plots using turtle.py. Turtle is a package based on, it's sort of like Logo, and it's included when you install idle. So this will work in idle or in here, since I installed idle, but it won't work in Sage. Sage is just use the regular plot command they have there. Using the turtle.py package from idle. And by the way, if you want 3D graphing, you're going to have to use something called Vidl or Visual Python, or even I think there's a PI3D package also from idle. So idle is, you can do 2D graphics with turtles, and Vidl you can do 3D graphics and animations and all kinds of simulations and like projectile motion problems and stuff, and planet orbits and body simulations and orbits and stuff. Okay, so how about this? This is what I want to do. I want to graph the function x squared minus 2 and the tangent line at x equals 1. So let's figure out the tangent line at x equals 1, okay? So if f of x is, what was it, x squared minus 2, then f of 1 would be, let's see, 1 squared is 1 minus 2 is negative 1. So f of 1 would be 1, a negative 1, right? So x1 is 1, and, whoops, and y1 is negative 1 when you're doing y minus y1 equals m times x minus x1, the slope of the equation of the tangent line, or any line in point slope form. But then f prime is simply 2x. So f prime at 1, the slope for the tangent line, the m, right, is going to be 2, isn't it? Okay. So the tangent line, whoops, the tangent line to f of x at x equals 1 is, let's see, so it's going to be y minus y1 equals m times x minus x1. In other words, y minus f of x1 equals f prime at x1 times x minus x1. Which means, well, these comments are just notes, notes to self for humans talking to humans, and then the code here is humans talking to Python, and then the output in the shell is Python talking to humans, right? So there you go. All right, so you're gonna get y minus a negative 1. Y1 is a negative 1, so y minus a negative 1 is y plus 1, and the slope was 2. M is 2, so 2 times x minus x1, and x1 is 1, right? Which gives y plus 1 is 2 times x minus 2, or y is 2x minus 3. Okay, so what I'm going to do is I'm going to define a function, g of x, to represent the tangent line, which is 2 times x minus 3. And so I'm going to design my plot command so that I can plot not just the function, but anything, more than just one function, right? So here's the plot command. Define plot size. What I mean by size is sort of like when you do zoom standard on the TI 384, it gives you an x min of negative 1 and an x max of, an x min of negative 10, an x max of positive 10, and a y min of negative 10, and a y max of positive 10. Well, let's say size is 10, right? But I can make it any size I want. So this is going to give me a graph where 0, 0 is always in the center of the screen, and size is how wide it is. So if size is 5, it's going to go from negative 5 to 5 on the x-axis, and negative 5 to 5 on the y-axis, and so forth. Okay, so let's define that. All right, so the first thing I got to do is set up my canvas that I'm drawing on. And to do that, you have to import all the turtle functions, right? But anyway, let's do a set world. We're going to do a from turtle import everything. World. Set world coordinates. to negative size, comma, negative size, the bottom left-hand corner of that square window. So that's really x min, y min, right? Comma, size, comma, size, which is the top right-hand corner of the window, which is x max, y max. So like, you know, negative 10, 2, 10, 10, that kind of thing, if size is 10. Okay, and let me see here. All right, let's leave it like that. Save it. Okay, let's see what that does. Does that actually show anything? Let's see. It doesn't show anything yet. Okay, I guess it's not going to show anything until we start graphing. All right, so we go. Actually, that's weird. It didn't. Oh, I didn't call plot. Okay, I got to call plot. That's why it didn't give me an error. It's probably going to give me an error. All right, so to test what I'm doing, I'm going to say plot. Now, let's see. We're doing x squared minus 2, which has a y min, or turning point at y equals negative 2. And we're doing 2x minus 3, which has a y-intercept of negative 3. How about a size of 3? All right, let's see what that does. I'm expecting an error with set world coordinates. There it is. All right, so it did all the calculations up to the numerical integral and everything, and then it died at set coordinates. So what I got to do is go back to my imports. From turtle, import. And there's going to be a whole ton of stuff, so I'm just going to import everything. Star. All right, let's save that. Let's get back down here. And so we're just setting up the coordinates. I would think at least to show me the canvas, right? Clear. And there it went. Ah, yes. All right, the thing is the canvas disappears right away unless you put like a little delay in it. Let's put in a little delay called main loop. The main loop is going to be like the last thing in the whole function. So I'm going to leave that on the bottom and then just fill in stuff in between, right? So, I don't know, let's call this a delay. Save it. Let's see what that does. That's weird. What happened? Something weird happened there. Why didn't it do anything? Maybe I have to graph something first. All right, so how about we graph an x and y axis, right? All right, so now remember this is logo. It's also called turtle graphics. So the first thing I'm going to do is I'm going to hide the turtle. I don't want to see it. So hide turtle. There you go. I mean, you don't have to, but I prefer to do that. And then let's do the x-axis. How about that? Let's draw the x-axis. All right, so now it defaults to pen down. When the turtle moves around on the screen, you can set where it starts. You can make it go forward. You can go turn right. You know, that all kinds of stuff. Turn right a certain angle in degrees. Go forward a certain number of pixels or whatever. A certain number of units in the world coordinates. But then, you know, I don't want to see the turtle. So I'm sorry. I don't want to see it drawing yet. I think it starts in 0, 0 by default. I want to start at negative 3, 0 and go to 3, 0, right? Or negative size, 0 to positive size, 0, right? The x-axis right down the middle of the screen. So if I need to do what's called a pen up so it doesn't draw, in other words, it's a turtle. It's a weird turtle with a pen on its tail. So when it walks, it writes when pen is down, but it doesn't write when pen is up. Okay. All right, so let's make the axes a certain color just for fun. How about green? Okay, so the axis is going to be green, and let's set our starting position to negative size, 0. In other words, in this case, negative 3, 0. And let's go forward. Let's put the pen down, and let's go forward 2 times size. All right, let's see what it does. All right, so let's save it. And let's run it. It still goes away. Why doesn't main loop work? I used main loop before to make this. That did work before. Well, if you run this in idle, I think the graph persists. So you could run this in idle if you want. But I had this working in the shell on the command line just like this. What did I do something different? Wait, what did I forget? I set the world coordinates. I hide the turtle, pen up, color, set pause, pen down, forward. That's it, right? Then do the same thing for the y-axis. Then do a loop for the function, f of x. Then do a loop for the tangent line, g of x. Okay. And that's really strange. Well, you saw the x-axis, right? So this is working. If we have to run it in idle, we'll run it in idle. But this is weird. Why isn't it main loop working? Oh, main loop. Main loop. Wait, hang on. Main loop is a function. Why didn't it come up with an error? Did it come up with an error? No? It didn't recognize main loop. That's why. Okay, save that. It's a function. Duh. Let's see if that's all it was. Okay, there it is, right? There it is. Good, perfect. Okay. All right, let's do the same thing for the y-axis. There's a lot of ways you could do this, but... All right, so let's just copy all this stuff from x-axis on up here. There you go. But now it's going to be the y-axis. Now the y-axis is going to... Notice how it defaulted going... Let's call it east, that's 0 degrees, okay? I want to go north. If I start at the bottom of the y-axis from 0, negative size, I want to turn north, so now it goes clockwise. So 90 degrees would be south, 180 degrees would be west, 273 would be north. That's what I want to do. All right, so pen up. Okay, so pen up. Where's my y-axis? Set position to... Color is already green, so I don't have to do that. Leave it at green. I guess I don't really have to do that. You could leave it there, I guess. It doesn't hurt. Let's start at 0, negative size. So starting at the bottom of the y-axis on my window, which is -3 to 3 for x min x max, -3 to 3 the y min y max if size is 3. All right, before we put the pen down, let's turn right to turn 270 degrees, like we said. Then pen down, then forward to 2 times size, and that's it. Okay, I think that's it. Okay, so let's see if that gives me the y-axis. Just showing you how this works, taking it slow. X-axis, y-axis. And when you don't do the pen up, pen down stuff, it'll draw from the end of the x-axis to the beginning of the y-axis. You don't want that, okay? So that's what the pen up is for. And when the pen down is down and the turtle moves, it actually draws in whatever color you set. All right, now let's plot f of x. And you know what it looks like. X squared minus 2 goes through 0, -2 on the y-axis, and it's a smiley face, hold water parabola, right? So let's see. How are you going to plot? Let's do it here. Plot f of x. And you can make as many plots as you want. Call them f of x, g of x, h of x, whatever you want. Let's make it a loop. Let's see. First, let's do a pen up, so it doesn't draw anything. I got to set the starting position to the first point at negative size, comma, f of negative size. How about that, right? So, let's see. Let me think about this. Alrighty. Let's think about this. All right, so I got a pen up, right? All right, how about we color this graph? Let's make it red. Okay, let's color it red. All right, let's set the position. Set position of the turtle before it starts drawing before I do a pen down, to negative size, comma, f of negative size. Whether that's on the screen or not, that's where it's going to start drawing. That's good. Okay. Alrighty, I think that's done. And then let's do a pen down, so I can start drawing once I move. And what I'm going to do is I'm going to do a loop that cycles through different values of x with small increments throughout the loop, and calculate f of x and f of x and graph that each time. So how about we say x starts at negative size, and while, let's do a while loop, while, let's see, while x is less than or equal to size, let's do it this way. No, this way. Okay. While that's true, notice it indents some more, so whatever's indented here gets repeated in the while loop while that coordinate is less than or equal to size. Let's make x plus equals, I don't know, 0.1. Go by 0.1, look across the screen. You can make it smaller if you want. And then go to, make the turtle go to x comma f of x. And it'll draw as it goes. Perfect. And that should do it. I think that'll do it. Am I missing anything? I think that's it. Okay, so save that, and let's see if it graphs the parabola we were talking about. It might take a little while because the parabola starts off the screen at negative 3 squared is 9 minus 2 is 7, right? So it's, my y-max is 3 and it's starting at negative 3 comma 7. So, but that wasn't too bad. Okay, there's your parabola, and the roots here, the roots are at negative rad 2 and positive rad 2 probably, right? So that's what our estimates are. Anyway, so let's X out of that. And let's see, let's go back here. Now let's graph the tangent line, right? So how about we take all of the stuff we did for f of x, add to it another graph, right? But let's graph g of x instead. That's the tangent line we came up with, right? So there's g, and there's g. I think that's it. Okay, so this should add the tangent line. Control S to save, shell out, clear, run, x-axis, y-axis, f of x, and the tangent line to f of x at x equals 1, which had a point of tangency of 1, negative 1. Right, so it's hitting at 1, negative 1, and the y-intercept of the x of the tangent line is 0, negative 3. The y-intercept of the parabola is 0, negative 2. You know what? How about we make this graph a different color? Instead of making this color red, let's make this color blue. How's that? Okay, so the axis, whoops. What happened there? I didn't X out of this. Alright, the axes are green, the parabola is red, and the tangent line is blue. Axes are green, tangent line is red. Oh, sorry, the parabola is red and the tangent line is blue. Good. There you go. I think that's good. Nice. I like it. And you can change the size of the graph if you want. You could make it, I don't know, x min, x max is negative 1 to 1. Y min, y max is positive 1 to 1 if you want. Save it. Run it. You're going to not see as much, but there you go. Yeah, and I can see anything because the intercepts are off the screen and the point of tangent is off the screen, and the tangent's off the screen, the parabola's off the screen. That's terrible. All right. Didn't we say if we start at -3, it goes up to 7? How about, just for fun, let's make it 7. So the point, if this is -7, this is +7, this is like -3, 7's there. There you go. That's what we said about the parabola, right? That's 0, -2. There was your tangent line. And that's 0, -3. And there's a point of tangency at -1, 1. Let's see. You can't see that on here, can you? Can I do this? All right. So here is the y-intercept of the tangent line, 0, -3. Here is the y-intercept of the parabola, 0, -2. Here is a point of tangency, 1, -1. Where the parabola hits the x-axis is at rad 2, 0. And where the tangent line hits the x-axis is the second guess of Newton's method, which was about 1.5. Okay, as you can see here, right? And there you go. Okay, so I think that's it. I think we covered everything. So you know how to graph in an arbitrary window, arbitrary sized square window, I guess. You can get numerical derivatives, you can get definite integrals, you can get roots numerically. I think you can do everything you need to do for the AP exam on here. Alrighty, so. And again, you can run this in idle, and you can run this in Sage 2, and even in pure Python mode, if you click Python, except for the turtle graphic stuff. Okay. And I think we're done. Very good, thank you. Very nice. Let's see. Let's put this back. I like it at 3. Let's put it back 3. And let's graph that. And there you go, we're done. Alright, so there's your graph. There's your graph, right? Okay, and let's put that out of the way. F of the square root of 2 is about 0. F prime of 2 is about 4. The closest root to f of x is equal to 0 near x equals 1 is 1.414, rad 2-ish, right? And the definite integral of f of x from 0 to pi is 4.052-ish, which remember was pi cubed over 3 minus 2 pi, right? And then there's the graph of the parabola, x squared minus 2, and the tangent line using the derivatives to get all this fun information. And we are done. Okay, bye-bye YouTube. Have a great summer. That's enough fun for today.